Hey guys, welcome back. So in this video, let's discuss about the topic deep learning. So in our last video, we have seen how ML works. So the machine learning is only dependent on the input data, and it is going to apply some sort of a statistical uh, functions and some sort of uh, models and algorithms to sort of understand how the input is related to the output. Uh, but if we are trying to mimic the uh, human brain, then we have to create an algorithm which has to be inspired from how the real biological neuron works, right? So from this idea, we came to something called as the artificial neuron. So we wanted to create a very small in our brain, the smallest unit of information transfer is nothing but a neuron. So we wanted to implement that a neuron into our program. Uh, so so developers have created an architecture. So it is called as the artificial neuron. So this artificial neuron was created in such a way that it is going to mimic the behavior of a biological neuron. So how? So okay, then what is the working of this neuron? So the neuron is going to take some data from other receptors. It is going to do some sort of processing, and then it is going to transfer that a unit of information to other brain cell. So this is the actual behavior of the human brain. Then so we wanted to create the same thing. So first we went with something called as a perceptron, which is the actual this is the actual unit of a unit of this algorithm, which is responsible for computing and information. Okay, then okay, how does this work? So this works in a way that it is going to take inputs. So some inputs are going to be given, and each input is going to have a weight associated with it. So the weight is used to understand the the importance of that input. The some sort of inputs might be of a lesser importance. Then we're gonna assign some a smaller weight to them. If some inputs are of high priority, then we're gonna assign some high weight to them. So so by so by at, at, tuning these things, we are going to give an output which is expected of this a single neuron. So here we have two other components. So there is something called as a transfer function and an activation function. A transfer function will do nothing. It is going to just sum up all the inputs and weights, and it is going to give you a result, a number, and that number will be tested against the activation function, and the activation function is going to determine the output of the neuron. So what is this activation function? So there are actually these four are the main activation functions used in the deep learning. So this is the tanh activation function, and the ReLU, which is the rectified linear unit, and then we have sigmoid and linear. So linear is not actually used, but so these three are used in the industry right now. Then let's see what this network does. So we have seen what this single unit of neuron looks like inside. So it is going to have the a transfer function and the activation function, and then we are going to club together a lot of neurons and create a network. And this network mainly has a three layers. It's going to have the input layer, and then we have some one or more hidden layers, and then we're going to have a one output layer which is going to give you the exact output which is expected of it. So if we were to compare both ML and DL, so we are sort of doing the same thing. We are feeding some inputs to our model. So we are feeding some inputs to our model, and we are expecting the outputs, and we are going to test the outputs against the outputs that are expected. So we are sort of doing the same thing, but the model that we are using is now inspired from the human brain. So it is expected to mimic the human brain. So is it reaching the expectations of it? As of now, the feed forward networks are very limited, because this works well for the tabular data, but in real world, the amount of the data produced is not usually in the a tabular form, right? So the feed forward networks or the multi-layer perceptrons are only limited to work with the tabular data. So for using the data like the at time series data and text data, audio data, so we actually classify this sort of data as the sequential data. To work with the sequential data, we needed some other architecture, so which is nothing but the RNN. RNN is the recurrent neural networks. So this architecture is very much similar to the feed forward network, except that it has something called as a feedback loop. So which is uh, so this a feedback loop is going to help the model to remember uh, computations from the previous state. So it is going to preserve some amount of data from the output of the previous state to this current state as another input. So here we can see it is actually given as an input to this same perceptron. So we are going to hold some of the information about the previous state. So this is going to help us, process the sequential data. If you were to unfold what okay this is how this is typically how an RNN looks like. If we were to unfold it uh, at the time t minus 1, so this is the flow, and then we got an output, and this will be given as an input to the next timestamp, and then it works in the same way, and it is going to pass on the information to the next nodes as well. So there are mainly four types of it. So there is a one to one, a one to many, many to one, and many to many. So and then in RNN also we have another problem. So uh, so there is this a problem called as a vanishing gradient or exploding gradient. So what is this problem say about? So let us say in at this point of time, so we have inputted a data, and then after a few iterations, okay, at last in the 100th iteration, so whatever the information that we have processed in the uh, 0th interval is it's not going to be remembered by the model, so it is going to forget that. So whatever the information which was placed in the earlier inputs is going to be vanished, or there might be another case where the input was maybe of very high priority. It is going to be exploding. It will gradually increase its weight, and it is gonna make the model a bit disturbed, uh, as it was having an exploding a variation in terms of the inputs. So to solve this, we came up with something called as an LSTM, which is the long short-term memory. It has a few gates, so it is going to have an input gate and output gate, same as our previous modes, but it is going to have something called as a forget gate. So the a forget gate is used to forget the information which is not relevant as of now. So it is used to eliminate the exploding gradient, and then we have the input gate. So it is going to manage all the inputs. So it is going to ensure that whatever the previous inputs are there, so they are also given some sort of priority, so that we can eliminate the problem of a vanishing gradient. So this architecture works well up to some extent to sort of provide uh, a an algorithm for a sequential data, but it actually fails when we are using the a sequential data like a text. So what happens with text? So when we process text, so it is not the same case that the of context with which the a text is to be processed. It could be a unidirectional or bidirectional. So we wanted to create another algorithm uh, which can scan the input from either of the directions. So we went with something called as bidirectional LSTM. So even though we weren't able to solve the problem of understanding the context of a text and remembering the context of a text. So in 2017 we came up with something called as an encoder decoder system. So the encoder system is going to encode the data and the decoder is going to decode. So using such an architecture, so we were able to preserve the context as well as understand the relevance of each inputs. So upgrading this model, uh, they have invented something called as the transform model. So the transform model is going to have an encoder and the decoder architecture. So this was primarily used for you know exchanging the languages and letting the system translate the languages. But later it was used to process the text as in the context was needed. So if we were to if we if, so so this is the base working of how a transformer works. And if we were to go into the encoder and the decoder, so we have such a architecture with a multi-head attention and add and normalization layers. So these layers are defined in such a way that they carry the information in the form of QKV. So these are nothing but a few vectors. So these vectors are going to provide you with the attention that you need to give for a specific uh, input text. So the amount of attention that was needed is going to be calculated in the multi-head attention, and it will be sent to a feed forward network for preserving the output as a probability unit, right? And the same transformer is going to be used by the GPT. So the GPT is going to use only the decoder only architecture, and Google's BERT is going to use the encoder only architecture, and then the Meta's Llama is going to use a similar architecture, but it is going to use the assembly called as the masked multi-head attention. So using this architecture, it can preserve more of the context than the information of the context. So each one has its own disadvantages. So in the next video, we'll see about the large language models.